Good afternoon, and even though it's really good morning from where I live, near Boston area. And first I would like to thank the organizers for the invitation to give this talk on a QKD protocol that is capable of achieving gigabit per second secret key rates. So I will start by showing you just a brief introduction that in terms of secure communication or transmission of classical information, the one-time pad encryption is well known to be actually impossible to crack. Now, I'm not going to go through that. I mean, you can read about it, but the important thing in order to do that is that Alice and Bob must share the same truly random keys. That's one. And then these keys must be as long as a plain text message. But more importantly is you can only use the secret keys only once. So if you follow these rules, then the one-time pad is perfectly secure. So if that is the case, then the problem becomes that you have to distribute the keys securely. Okay, so instead of worrying about transmission of the message, you're worrying about the transmission of the keys. So, and here comes, quantum key distribution. The idea of calling it a quantum key distribution is that the protocol allows you to detect the presence of the eavesdropper, okay, and then therefore allows you to actually reduce her knowledge of the generated keys to practically zero. Okay, that's the whole idea of quantum key distribution. Now, the concept of QKD is actually based on the known cloning theorem that I think most of us agree on. And the idea is that if you have an unknown qubit and you want to make a copy, it's just impossible, okay? And if you have the right protocol, then if Eve is trying to measure this unknown qubit, she would inevitably create a disturbance that is detectable by Alice and Bob if you use the right protocol. So the whole point of the QKD being quantum is that the laws of quantum physics, using this no cloning theorem, allows you to guarantee the QKD security. The important thing is that you have to understand is that non-classical resources, such as entangled photons, is not necessary, okay? So that's why, for example, when we give talks about BB-84 and other things, they say, where's the quantum part, okay? The quantum part is really in the no cloning theorem. So let's quickly review the state-of-the-art demonstrations. Andrew Schultz of Toshiba have demonstrated some years ago that for a 10 dB loss channel, they have achieved something of the order of a little bit over 1 megabit per second. And then J.Y. Pan in China showed that for a LEO satellite to ground using, again, decoy state BB-84, they achieved something a little bit over 1 kilobit per second. So these are actually very low rates for practical applications. The problem is that when, think of it as the BB-84, when Alice sends a bunch of photons to Bob, okay, so let's say you have, you're able to generate single photons, perfect single photons. By the time it reaches Bob, because it's a 10 dB loss channel or however what the attenuation is, the number of photons that arrive at Bob's detector is going to be much smaller. So fundamentally, because of security, you send less than 1 photon per bit in general on average. Otherwise, there would be so-called photon number splitting attack. So given the component losses and propagation losses, you actually receive very low secret key rates. You achieve very low secret key rates because of that. And in fact, there are rules or limits that have been proven to show that how the rates that you can, maximum rates you can achieve as a function of your loss is shown in this paper. So the question that, how do you, scale it up to, let's say, gigabit per second? So if you think of the BB-84, what you can do is that instead of one channel running at, let's say, 1 gigabit per second rate, you can dial it up to 100 channels and running at 10 gigabit per second rates. But then you would encounter a lot of problems in terms of the complexity. You have to deal with the timing, the control, as we heard in the previous talk. There are a lot of things you have to deal with. And there's post-processing for each channel. And then there's cost, especially if you're talking about using superconducting nanowire single photon detectors. So let's look for solutions in terms of what classical communications would do in such what we call photon staff situations. A is that they would send a lot more photons per bit for redundancy, so there will always be some photons reaching the endpoint. They also use erbium-doped fiber amplifiers as the repeaters to replenish and extend the transmission range. Even at the detector stage, you use EDFA preamps to restore the signal-noise ratio. So the question is that, can we use similar techniques in QKD, but of course, without compromising the security? Sending more photons per bit, using EDFA to mitigate the channel loss, and maybe we don't even need single photon detectors. Now, that sounds like heresy, right? Nobody would think of using amplifiers in anything quantum. So here's the new protocol that at MIT we came up with. It's called Floodlight Quantum Key Distribution Protocol. It's radically different. So first of all, instead of a one-way protocol, it's actually a two-way protocol, and we break many of these conventional rules. But what it does allow us is to actually achieve a much higher rate. So let me explain. So first of all, we actually use many photons per bit, but over many, many modes. The important to understand is that no cloning theorem is not pertaining to per bit. Doesn't care about per bit. It's about per mode, okay? Each mode is different. So if you spread the number of photons over many, many modes so that the mean photon number per mode is actually less than 1, then you maintain the security that is afforded by the no cloning theorem. 2 is that if you have a lot of photons coming in, then you don't need to use single photon detectors. You can actually use homodiode reception, okay, as we'll show you later. And that makes it much easier to handle the key generation. And finally, we actually would be using an EDFA, an amplifier, at a strategic location so that it helps mitigate the channel loss, especially this is a two-way protocol. And here's some references. The first one is the theory of the Floodlight QKD protocol. And then we have a proof of concept demo at 100 megabit per second, running at 100 megabit per second rate. And then finally, 2 years ago, we have demonstrated running at over 1 gigabit per second secret key rates. So let me start with how this two-way protocol works, okay? This is not your standard, one-way protocol, which is shown in here. So the one-way protocol, think of this as standard one-way. Bob sends something to Alice, okay? And there's a Eve in between to try to eavesdrop. The two-way protocol is a little bit different, okay? Instead of starting from Bob, we actually start from Alice. So what Alice is doing has a broadband source, which is a amplified spontaneous emission source, very broadband, send a little bit of that light to Bob. And of course, we assume that Eve is in the middle, taking all the light that is being lost, okay, in both directions. And right now we assume that it's a passive Eve for now, okay? So Bob is now doing the same thing. So the first thing to remember is that the first part, Alice sending this light to Bob, has no information, has no message, has no keys, nothing. It's just a source, okay? And then Bob would do let's say, a binary phase shift keying. That's when you encode the key message, okay? And then he would use an amplifier to amplify the signal, because in sending it back to Alice that goes through a loss channel, he would like to have the signal noise ratio maintained, okay? But remember, this amplifier also add additional noise. So there is sufficient noise added that it would be okay, okay? Now, back here, Alice will use a homodyne receiver to detect this message. And the reference is actually coming from the ASE source originally, and then there's a delay line so they we match, and then that serves as a local oscillator for the homodyne receiver. So in the actual experiment, what we have is that for the ASE source is actually a EDFA with no input, and we use a core WDM filter to carve out the 18 nanometers, about 2 terahertz bandwidth as a source, okay? And we impose, by putting attenuators, a 10 dB loss for the channel. The binary phase shift keying allows Bob to put in either 0 or pi phase shift, and then the EDFA is a 40 dB gain amplifier. Send it back, and there's a homodyne receiver which is using a standard InGaAs photodetector. For now, we assume that Eve is listening passively. So let's look at the performance of this. So this is the actual measurement. You see the data points as a function of the number of photons per bit that Alice sends. Now, we have the modulation rate is 100 megabit per second. So that means that 1 bit is about 10 nanosecond. And since we have a 2 terahertz bandwidth, that in each bit there are 20,000 modes. So we are sending about 200 photons per bit. That means that we are sending 0.01 photon per mode. Okay, much less than 1 that is needed for the security. The red line is what we have in theory, and you can see this is the bit array measurements that we obtain, that even at 200 photons per bit, we are reaching something of the order of 10 to the minus 2, so it's no problem in decoding the message perfectly, okay? And you can see that the bit array can goes down to 10 to the minus 5 easily if you increase the number of photons per bit. However, you don't want to do that. What we plot here in the green dashed line is the calculated bit array for Eve, assuming that she has, first of all the light that is being lost in the channel. So that's for 10 dB channel, that means that she grabs 90% of the light that is going from Alice to Bob, and also from Bob back to Alice. And we assume that she has the optimal quantum receiver in, so this is essentially the so-called channel bound. And you can see that if you send too many photons per bit, she would be able to actually have a pretty good bit rate. For example, down here, if you have let's say 800 photons per bit, then she would have a bit rate of 10 to the minus 2. That means that she would also be able to decode the whole thing. However, if you work at a much lower photons per bit, let's say 200, Alice would still be able to decode everything, but let's look at what Eve can do. Eve is essentially around 1/2. Now, what is 1/2? 1/2 when she is simply guessing, 1/2 is 50%. She is simply guessing is it a 0 or 1. So she has actually absolutely no information whatsoever. Now, this is our actual trace of our measurements. The red is the Bob's message bits, 0 and 1 in the binary phase shift keying. The blue is what Alice actually received, and you can clearly see that she would have, well, first of all, she has very high signal noise ratio, and she will have no problem in decoding the whole message. Now, so far we have assumed that Eve is actually a passive Eve, but let's assume that Eve is actually smarter than that. That she says, well, this two-way protocol, there's a very easy way for her to pretend to be actually Alice. So what she would be doing is that she would also sends in light, okay, right over here into the channel, okay, and then Bob would do his stuff, and then on the way back, Eve would take that message and she would be able to decode everything, just like Alice. So that would be a problem. If we do it this way, then the protocol is completely broken. So what do we do? Again, let's go back to think about what classical communication can do. What classical communication would do is that they would always have channel monitoring, and that's exactly what we're going to do, okay? So here's the way we want to do the channel monitoring. We would Alice would have a spontaneous parametric down conversion source creating photon pairs, okay, time coincident photon pairs, signal and idler. She would retain the idler, measure it with a single photon detector, and then the signal would then be combined with the ASE source and send it to Bob. Okay, now the important thing is that as far as the spectrum of the signal photon of the down converted source and the ASE source, they would be completely identical, so that Eve would not be able to tell whether the photon that is coming through, which is at random, is belonging to the ASE source or to the signal source. Now, when Bob receives that, he would tap a little bit of that and send it to a single photon detector. And the idea here is that the signal and idler, you would measure both the signals and also the coincidences between what Bob measures, which is the signal photon, and what Alice has, which is the idler photon, okay? So the point is that if Eve is sending her light in, okay, her light and the idler photon will have absolutely no correlation. There's no coincidences, okay? And we'll see later on that by measuring this coincidence between the two, they will be able to detect whether Eve is sending anything in, okay? So that channel monitoring would essentially prevent Eve to send in light to try to pretend to be Alice. Now, the other thing that I would show you is that Alice would actually do a little tap here before the light goes out, so it's entirely within Alice terminal, and also to do the coincidence measurement. And this is really to eliminate the need for calibration. So let me show you how that works. Okay, this is the detailed experimental setup. It's a little bit complicated. So here's a EDFA. It goes through a CWDM channel, okay, so to carve out the 2 terahertz band. And then we attenuate it so that very little light, less than much less than 1 photon per mode is sent to Bob. Bob would send in the message, tapped it, and then it comes back. Now we see that there is also 2 CWDM filters here, and that is to prevent any out-of-band message that Eve is trying to send in. So the whole thing is actually a giant interferometer. It has to be phase locked for the homodyne reception. Here's the LO, and we have dispersion compensation both here and also using a wave shaper for fine dispersion compensation. Now, to test whether the channel monitoring works is that we tap a little bit of light from here, delay the time so that there's no real correlation, and then use that as a injection for Eve. And here's the, we're using periodical lithium niobate down converter to generate signal at 1550 that also goes through the same filter, so they have the same spectrum, and then the idle is 1570. And we're using superconducting nanowire single photon detectors for the detection, and then we measure the coincidence. And again, as I mentioned, that Alice terminal also have the tap. So let's look at the measurement results. So here's the measurement. The blue is the within the tap between the Alice idler and the Alice tap of the signal. And you can see this is the background coincidence count, and then for the right timing, this is a function of time, you can see that there is coincidence between the signal and idle, a very sharp peak, so that we monitor that. Now, the red line is between the idler of Alice and Bob's signal photon, the measured photon that he measures. And again, you can see this as a sharp peak. Now, what happens is that is for the green line that is of interest. The green line is when Eve takes all of the light that is going from Alice to Bob, and she was sending her own light, okay? But remember that her own light has no correlation whatsoever with the idler light that Alice has. So that you can see that here is all the coincidence count, but there is no peak, okay? So the idea is that this channel monitoring would ensure that Alice and Bob would have measurements to check whether Eve is sending anything in. So how well can we do? So again, remember in the diagram, we show that we are injecting light for Eve. So here is the amount of light that we know that we're injecting into the channel. And on the y-axis is the measurement that we estimate the amount of light that Eve is injecting. And you can see is a really very, very good correlation with some error bars. The error bars is essentially what we are able to detect, okay? So for example, down to the case where we're actually not injecting any light into the channel, and the estimate is that we're able to measure within roughly about 0.25%. So with this channel monitoring, we can actually know how much Eve is injecting, okay? And from there, we can actually estimate the amount of information that Eve is getting. So let's look at the actual measurements. So this slide is a little bit complicated, but you know, for people who are doing QKD, this is fairly standard stuff. So the first thing to think about is that the mutual information between Alice and Bob. So this is essentially the light that Alice received and she was able to decode. And this is the green line here, okay? These are the data points, and this is the theoretical curve that we expect. And so you can see that if you start sending more photons per bit, she would be able to decode most of the stuff. And 100 megabit per second is the modulation rate. So, but you have to assume that there is some reconciliation efficiency that we assume that is about 94%. This is for sifting and all kinds of stuff. And also you have to subtract the light subtract the information that you think that Eve is getting. This is the so-called level information shared by Bob and Eve, okay? And depending on whether you assume that Eve is just a passive Eve or is an active Eve. So if you have just you're assuming that Eve is just passively eavesdropping, that is this dash black line here that we estimate that Eve is getting. And you can see that as you transmit more photons per bit, that she would be able to get more and more information. If you send in too many photons, she'll be really getting all of the information. So that's not a good idea to do that. Now, if you assume that Eve is actually an active Eve, in this particular case, Eve is actually not sending anything in. Okay, so is zero injection, but our estimate is only good to about 0.27%. So we're assuming that Eve is injecting light up to about 0.27% on average. And this is the brown dash line. Clearly, she would be able to obtain more information as you transmit more and more light. The useful information, which is the secret keys, is when you subtract that. This is the delta IAB here, the secret key capacity, when you multiply by the modulation rate, would be your information rate, which is in this particular case, the blue curve here or the gray curve here. Blue is when you're assuming that is only passive eavesdropping, and we obtain about 66 megabit per second when we are driving, when we are sending only 200 photons per bit. Okay, and if you assume that it's an active Eve, and we receive about 55 megabit per second. So the important thing is that to remember is that this is more than a factor of 10 in comparison with the best that has been demonstrated for a 10 dB channel loss using BB-84. So then 2 years ago, we increased the rate using higher speed components. We're then using 7 gigabit per second modulation rate, pseudo random bit sequence, homodyne receiver that is much higher bandwidth. One more thing that I haven't mentioned, but it should be is part of the protocol, is that at the receiver side, the noise is being dominated by the ASE source noise from Bob's EDFA, so that it is not critical to have a homodyne receiver that is short isolated. So that is actually a good thing. So again, we have 10 dB loss channel, both from Alice to Bob and Bob to back to Alice. And this is just a sketch of what it looks like. And, it was reported in this journal 2 years ago. And again, so at 7 gigabit per second, the bit duration is about 143 picosecond, and for 2 terahertz bandwidth, we have roughly about 900 temporal per bit, and we are sending only about 20 photons per bit. So it would still be much, much less than 1 photon per mode to make sure that the security is maintained. The bound on ejection fraction is about 0.25%. So in this particular measurement, there's no actual injection, but we assume that our channel monitoring is only capable down to about 4%. So the mutual information measurement is shown in this blue curve. The dash curve is what Eve is able to get. That's the whole label information. And the difference is, of course, the secret key rate, that at 20 transmitted photons per bit, we are receiving about 1.3 gigabit per second secret key rates. So this is now 3 orders of magnitude higher than what the standard BB-84 can do. So let's look at the some implementation issues if you want to do a practical measurement in the field. So remember, this is a two-way protocol, and you need phase stabilization. You need the time delay of the LO-side and the signal path to be matched. So one of the things that, because we're doing homodyne reception, is you need a phase stabilization of the entire thing. So of course we did the measurements in the lab, so that's easy. But in the field, then luckily in 2017, our colleagues at MIT Lincoln Lab and demonstrated a phase log loop between Lincoln Lab, which is actually something like 40 kilometers away, using a dark fiber that the round trip is about 86 kilometers, and we have successfully phase logged the signal. So we're able to do that. Now, if you want to do it in free space, that would be much, much tougher. So I think in fiber loop, in a metropolitan kind of distances of, let's say, 50 kilometers, this is perfectly doable. Now, because we have the two minutes,
2 minutes left. Sorry, Franco, for interruption.
Thank you. It's a short coherence length, so it's about 0.1 picosecond, so you need to match the path length. Again, it's essentially demonstrated previously in 2017 for these distances. You need to worry about the dispersion compensation, but that doesn't change over time, so that's not a problem. One of the issues is that for channel monitoring, you really need something that has fast recovery times. In fact, in the nowadays, we're actually using faster recovery times. But also, you can use tricks like using multiple detectors, and this be demonstrated in 2013 that you can even get about 100 megacounts per second. So that makes channel monitoring much easier to handle. Now, I want to show you a comparison between BB-84 protocol and our protocol, the Floodlight QKD, both in terms of the security and also key generation. So let's look at the key generation first. In both cases, we're actually using classical light sources, using weak laser light for BB-84, and we are using weak broadband light. Okay. And the number of bits per, the number of photons per bit used, of course, for BB-84, you need to be less than 1. We are much more than 1. That's the whole point. You spread it over many modes to mitigate the channel loss. The detection usage is that the BB-84 use single photon detectors. We are using homodyne reception because we have many, many photons in the reception area, in the receiver. In terms of operation, the BB-84 is very simple. It's a one-way protocol. It's much more complicated. In our case, it's a two-way. You need the phase locking. On the other hand, in our case, we're able to generate over 1 gigabit per second for a 10 dB channel loss. That's not possible, even theoretically, for BB-84. In terms of security, we are both using physics-based security based on the no cloning theorem. In BB-84, that's it. In our case, we need channel monitoring to make sure that the active eavesdropper is essentially absent, and all we need is to use photon pairs and single photon detectors for that purpose. So in summary, this is a new protocol. We break some conventional rules in terms of using EDFA, how many photons per bit, and that allows us to achieve circuit rates much, much higher than what conventional BB-84 can do. Looking forward, we can actually double the bit rate by using quadrature phase shifting, and also something that I don't have time to talk about, but you can look at this reference here, and you can actually use this whole idea even when encryption keys are compromised, so-called quantum low probability intercepts. So finally, I want to say that I'm not the person who did all the work. The theory was headed by Jeff Shapiro at MIT with major contribution from Zhesheng Zhang, who was a postdoc in our group, but who is now a faculty member at University of Arizona in Tucson. He is also the main experimenter in the experiments carried out at MIT. So that's all I have. Thank you very much.
Thank you very much, Franco, for this exciting talk on this special topic. And please all open up your mics and applaud Franco.